You don't need a second.
Devastating conflict of the 20th century, Germany developed a structure of unprecedented research and innovation. Beyond the military, the National Socialist regime also gave rise, directly or indirectly, to innovations that are still surprising today for their scope and permanence. The popular Fanta soft drink was created in Nazi Germany as an alternative to Coca-Cola following the trade embargo. Night vision, a key technology in modern operations, had its first practical applications in the tanks and weapons of the Third Reich. The concept of the intramodular module, fundamental to modern industrial manufacturing, was explored to optimize war production. Even cultural and sporting elements were born or institutionalized at that time. The Olympic torch, which became a global symbol, was introduced into the 1936 Berlin Games under a stage design designed by the Nazi propaganda apparatus. Furthermore, the rivalry between the Dassler brothers, regime collaborators, gave rise to the Adidas and Puma brands, icons of contemporary sport. These examples demonstrate that, amidst authoritarianism, developments flourished whose influence persists long after the end of the Third Reich. Volkswagen Beetle, the car born on Hitler's orders. In 1934, the German government was looking for an affordable car that any family could afford. Hitler commissioned the design to Ferdinand Porsche, who had been working on vehicles for some time. The plan was to have a simple, economical and reliable car. That same year, they signed an agreement with the German Automobile Association to begin the project. The car was named KDF Wagen, after the regime's Strength Through Joy program. It was to cost less than 1,000 marks to make it affordable for everyone. Over the next few years, Porsche and his team refined the design. In May 1938, they organized a large event in Fallersleben. Hitler laid the foundation stone for the plant that would manufacture the car. That location later became an entire city, later named Wolfsburg. At that event, it was announced that the factory would not only make cars, but would also be used to promote the idea of a modern Germany. The car was not only a means of transportation, it was also part of the image the regime wanted to project at home and abroad. When war broke out, the civilian model was discontinued. Instead, they adapted the design to create vehicles for military use. One of these was the Kubelwagen, a rear-wheel drive Jeep-like vehicle which was used on several fronts. They also released the Schwimmwagen, which was amphibious and could cross rivers and lakes. Throughout the war, not a single unit was sold to the public. All production went to the army. Although thousands of people had paid in advance for the civilian car, they never received it. The priority was the front lines. At the end of the war, the factory remained in British hands. Instead of closing it, they decided to continue with the model that had already been designed. From then on, production began on the car that would later be known as the Volkswagen Beetle. The car that had been born as a project of the regime ended up being one of the best-selling in the world. Its design, S by MIT, was around for decades and was manufactured in several countries. Its rear engine, rounded shape and distinctive sound made it recognizable across the globe. What began as a commission from the Third Reich eventually became a symbol of civilian transport. Although its origins are directly linked to the dictatorship, the Beetle enjoyed a second life after the war, no longer for propaganda or political purposes. The Olympic torch, a Nazi invention that lives on today. In July 1936, the fire was lit in Olympia with a mirror made by Zeiss. A woman dressed in a white robe lit the torch using concentrated sunlight. From there, it began the journey of more than 3,000 kilometers to Berlin. The idea for the relay came from Karl Diem, the organizer of the Games. He was inspired by ancient Greek rituals, although they never actually existed. He planned for more than 3,300 people to run 1 kilometer each to carry the flame. From the beginning, the Nazi government used it as part of its image campaign. Goebbels arranged for everything to be recorded and broadcast on the radio. Leni Riefenstahl also filmed parts of the route for her documentary. The torches were manufactured by the Krupp Company. They were made of steel and carried a type of fuel that could withstand wind and rain. The mirror used to light the first torch was made by Zeiss Optics. The route passed through Greece, Bulgaria, Yugoslavia, Hungary, Austria, Czechoslovakia, and Germany. In Austria, the torch was greeted with Nazi salutes and flags. The entire journey took place from July 20th to August 1st, when Fritz Schilgen entered the stadium and lit the cauldron. Hitler was part of the opening ceremony that day. Schilgen was chosen not for his athletic achievements, but because his running style fit the image of the type of person the regime wanted to portray. The goal of the event wasn't sporting. What they sought was to connect the image of Nazi Germany with classical Greece, to appear heirs to that culture. They wanted to show organization, power, and unity to the rest of the world. Many people thought it was a peaceful and novel gesture, but in reality, it was a setup designed to spread the regime's message, using symbols, cameras, and the media, all well planned to reinforce Nazi propaganda. After 1936, the torch relay was repeated at every Olympic Games. Although it began as a staged event created by the regime over the years, it became part of the official Olympic ritual. Regime sneakers, the true story behind Adidas and Puma. In the 1930s, two brothers named Adolf and Rudolf Dassler owned a sports shoe factory in Herzogenaurach, a German city. There they produced sneakers in a family business they shared. During the 1936 Berlin Olympics, Adolf Dassler arranged for American athlete Jesse Owens to compete wearing his sneakers. Owens won several medals, bringing the factory worldwide attention. The company operated under the Nazi regime. Like many other German companies of the time, they also manufactured products for the military. The business remained active throughout the war. Both brothers were members of the Nazi Party. Their factory continued operating during the conflict, producing boots and other items for the armed forces. Collaboration with the army was part of their daily work. But in the midst of the war, arguments broke out between the two. Adolf and Rudolf's relationship broke down. After the conflict ended, they each went their separate ways and decided to start their own business. Adolf founded Adidas. He used the first letters of his first and last name to name the new company. He stayed in the same city and set up his own factory. Rudolf went across the river and started a different company. Initially, he called it Ruder, but later changed the name to Puma. He also focused on athletic footwear. Both brands were born in the same town and came from the same family. But from that moment on, they became direct rivals. The feud between the brothers caused even neighbors to split. Over time, Adidas and Puma became two of the world's largest sports brands. But their origins date back to the years of World War II, when they were still working together in a single factory. The sneakers worn by Jesse Owens in 1936 were made by them, before either brand existed. That Dassler factory was the beginning of everything that would come later. During the early years, both Adidas and Puma grew rapidly. They used their contacts, their experience, and the models they already knew to create new products. The foundation was the same they had used during the regime. Although they later distanced themselves from their past, the two brands started in the same place, in the middle of the war, under a government that included them in its industrial system. Today, they see themselves as lifelong rivals, but the story began with two brothers who shared a factory, ideas, and sneakers. And it all began in Nazi Germany. Künsch's nail, the medical tool that changed the war. In 1939, German physician Gerhard Künsch devised a different way to repair fractures in the body's long bones. He used a steel tube placed inside the bone's canal to hold it firm while it healed. This metal rod was then inserted directly into the center of the damaged bone. Before that, when someone broke their femur or tibia, the most common approach was to leave them lying down for weeks, with the bones stretched by a system of pulleys and weights. This method didn't always work, and it took a long time for the patient to walk again. With the nail Künsch proposed, the broken bone was fixed from the inside. This prevented it from moving and helped the body reattach it without having to keep the patient immobile for so long. It was completely different from what had been done until then. The design was simple, a metal rod with slits at the ends, which was inserted through a small surgical cut. Using special tools, doctors fitted it inside the broken bone and left it there to act as support. Künsch presented his invention in military hospitals, but at first it was not accepted by all. Many doctors still believed that bones could only heal if left untouched. However, within a short time, his technique began to prove that it worked better than what had been previously used. During World War II, the German army began using this method with wounded soldiers. Those who fractured their legs could get back on their feet within a few weeks, something that had previously seemed impossible at the time. This led to the nail's increasing use. Meanwhile, in other countries, the invention went unnoticed for a while. But when the war ended and Allied doctors saw the results, they began to copy the technique. Soon, the intramedullary nail became common outside of Germany as well. Künsch's model served as the basis for many other similar devices that followed. From then on, surgery for broken bones took a complete turn. It was no longer necessary to keep patients bedridden for months or use casts that immobilized half the body. Furthermore, the method helped reduce complications. Because the injured were mobile more quickly, the risk of infection, blood clots, and loss of muscle mass decreased. All of this gave the invention an important place in medical history. Although it was created in the midst of war, the Künsch spike was not a weapon, a vehicle, or a radar. But it allowed thousands of wounded German soldiers to return to the front or recover without becoming disabled. It was a tool used to keep the troops on their feet. The idea of inserting a metal rod into a bone seemed risky. But in practice, it worked better than anything that had come before. This led to its widespread use not only in Germany, but also in civilian hospitals in other countries after the conflict. Today, the technique has changed, but the basic idea remains the same. The nail Künsch invented was the first step toward what is now known as internal fixation. His invention remains part of modern fracture treatment. What began as a solution to speed up soldiers' recovery ended up being a real improvement in general medicine. And although few people know it, this breakthrough emerged from an operating room in the heart of Nazi Germany. The V1 and the Reichenberg, from the flying bomb to the piloted suicide missile. It can be said that the origin of the V1 was when a useful engine appeared. Because if a useful engine hadn't been available, it's likely no one would have come up with the idea of a flying bomb, or if they had, they wouldn't have taken it seriously. What decided everything was having a simple, cheap engine that could push hard enough. That development began in 1927 and 1928 when an aerodynamics expert named Paul Schmidt conceived of a pulse engine. The idea wasn't so complicated if one had already had that inspiration. It was a tube with a grill with slats that opened and closed at the inlet, along with a system that injected gasoline and a spark plug to ignite it. This type of engine had a couple of drawbacks. For starters, it couldn't sustain itself at speeds below 300 kilometers per hour, so it couldn't be started from a standstill like a normal airplane. It also couldn't accelerate or slow down. It ran at a fixed speed, climbing from 300 to its maximum speed on its own. Once it reached its ideal speed, it continued at that speed without changing speeds. It also wasn't useful above 2,000 meters because there the air would become scarce and the engine would fail. And after 30 to 45 minutes of driving, the valves would be burned and damaged and the aircraft would lose its engine. So although it was a fairly ingenious form of propulsion, it didn't seem to be very useful in ordinary aviation. However, in 1934, the same Professor Schmidt proposed that this engine could be used to power an aerial torpedo. But that suggestion doesn't seem to have been taken seriously. In 1938, the German Air Ministry began to look more seriously at the issue of jet engines, and to make sure it didn't miss any opportunities, it commissioned the Argus company to manufacture one of the engines Schmidt had designed. Argus produced it, achieving a thrust of about 300 kilograms, and delivered it to the ministry. They played with it a bit, analyzed it, and seeing that the army was already tinkering with missiles at Peenemünde, they decided the Air Force should also get involved, but with more force. So they called in the Fieseler company to propose a design. And at the end of 1941, Chief Engineer Lusser submitted some sketches. They considered it, and on June 19, 1942, they authorized the development of the flying bomb. To throw people off the scent, they officially named it Flakzielgerät 76, a name that sounded like a practice target for anti-aircraft guns. Fieseler named it the Phi 103, as he did with all his models, but few used that name. In southern England, the bomb began to be called the Doodlebug. At the same time, the Argus company was commissioned to produce the engine, and the Walter firm, an expert in rockets and fuels, was tasked with finding a way to launch the device at over 300 kilometers per hour from the ground so that it could remain airborne. The project progressed quite quickly. The first successful launch of the FZG-76 was on December 24, 1942, in Peenemünde. Many failed tests followed until the problems were resolved one by one. The final design of the FZG-76 was a straight-wing aircraft with the pulse engine mounted high aft of the body and rudder. Inside the fuselage, from front to back, it had a propeller that measured the distance traveled, a warhead with 850 kilos of explosives and 3 types of detonators, a tank with 570 liters of cheap 75-octane gasoline, 2 compressed air cylinders that powered the tail and altitude control system, a 30-volt battery with 42 cells, a main gyroscope, and the servos and automatic controls. The procedure was as follows. The tank was filled, a charged battery was connected, compressed air was poured into the cylinders, and then the aircraft was taken to a metal-free area to calibrate the compass and set the course toward the target. It was then placed on a launch ramp. The ramp was a long, slotted tube, about 45 meters long, divided into sections that were joined with bolts and mounted on a concrete and steel base at the appropriate angle. The tube was open at both ends, and the rear end had a bayonet-like lock. A large dumbbell-shaped piston was inserted into the tube with a fin extending through the slot. A flexible sealing tube was placed in the slot to prevent leaks. Above the tube was a cart that supported the missile and rested against the piston fin. Then, a cart containing a combustion chamber and tanks containing hydrogen peroxide and potassium permanganate, along with 3 compressed air cylinders, was attached. This cart was connected to the rear of the tube with a locking system. Near the ramp, the distribution unit was installed on a metal support. There were more air cylinders, pressure gauges, and valves for managing the compressed air that powered the engine during startup and activated the fuel valve. There was also a transformer with a coil that sent current to the spark plug through a flexible cable. Once the missile was on the cart and tightly fitted to the piston, the operators would go to a nearby shelter and from there initiate the firing sequence. Air was blown into the engine to simulate flight, and the spark was activated so the spark plug would ignite the engine. After about 7 seconds of warm-up, the valves on the rear cart would open. This mixed the reactants and generated a jet of superhot steam inside the combustion chamber. The piston, held in place by a pin that broke under pressure, would begin to move through the tube, pushing the cart and the missile forward. The steam pressure would force the sealing tube to close the gap. The missile would be launched at over 400 kilometers per hour. Upon reaching the end of the ramp, the piston would fly out, the cart would release, and the missile would continue on its own, climbing at the same incline as the ramp and gaining speed. Each site had several pistons and 2 combustion carts. While one was in use, the other was being prepared. At the end of each launch, the chemical-stained base was cleaned with special suits and rubber boots. After the mass deployment of the flying bomb, an even more risky version was tested. The same structure of the Phi-103 was adapted to include a cockpit, basic controls, and a seat with a harness. This model was named Reichenberg and was designed to be guided by a pilot to the target. The main change was to replace the automatic system with a manual control post. The jet engine was still the Argus AS-014, mounted on the fuselage, but the internal space was reorganized to allow a person to enter. It had no landing gear or real escape capability. Testing began in 1944. Training versions without an explosive charge were prepared. To launch them, Heinkel He-111 bombers were used, which dropped the aircraft from the air. Some pilots managed to stabilize their flight after the drop and remain in a straight line, but the results were unstable. The cockpit was very cramped. There was no room for detailed controls or safety mechanisms. Although an ejection seat could theoretically be installed, a functional one was never implemented. Flying the aircraft meant assuming the impact would be final. The volunteers came from a unit called Leonidas, part of the Luftwaffe. They received training in simple gliders before moving on to the Phi-103R. They weren't told it was a suicide attack, but they knew they had no real way back. In practice, attempts were made to plan a landing, but the design didn't allow for it. The idea behind the project was to hit targets more precisely. Having a pilot eliminated the deviations that the original V-1 had. The bomb went directly to the target, guided visually. This, however, depended on the plane reaching the area with good visibility and without being intercepted. More than 170 Reichenberg aircraft were built. They were stored ready for use but were never deployed in combat. The Luftwaffe Supreme Command, although allowing testing, never approved its use in real operations. Allied advances meant they weren't ready in time. Unlike other weapons, this manned version of the Phi-103 remained a prototype. Its existence demonstrated the level of desperation of the High Command, seeking extreme precision at the cost of the pilot's life. The program was shut down without a single attack being launched with this variant. The V2 project from Peenemünde to London. In October 1942, the British managed to see an aerial photo showing a large artificial sandbank on the island of Euston, just off the Baltic coast. On top of this base, they had set up what appeared to be a concrete platform, and next to it a complex of buildings. This image was one of the first concrete clues that Germany was preparing something out of the ordinary. What they didn't yet know was that right there, in Peenemünde, the development of what would become the world's first ballistic missile was underway. The rocket being built there was the A4, later known as the V2, the next step after the V1. The project had begun much earlier, in the 1930s, with a team headed by Werner von Braun, a young engineer with ideas far ahead of his time, working for the German army. The goal was to develop a missile that could fly outside the atmosphere, move on its own, and hit targets hundreds of kilometers away. From the outset, the plan was ambitious. They wanted the rocket to rise under its own power, follow a programmed path without external guidance, and carry a heavy explosive payload. To achieve this, von Braun and his team focused on solving three key issues: a sufficiently powerful engine, a reliable control system, and a structure that could withstand the pressure of the journey. The fuel they used was a liquid mixture of alcohol and liquid oxygen. Powerful pumps were needed to move these two elements toward the explosion chamber. This system was powered by turbines driven by steam generated by a reaction between hydrogen peroxide and sodium permanganate. Once ignited, the engine released burning gases that shot out at high speed through a nozzle propelling the rocket upward. To prevent it from veering off course, the rocket had a system of gyroscopes that indicated its direction and small fins that rotated to keep it stable. They also used a system of rudders inside the engine jet to keep the aircraft on course during takeoff. Higher up, during flight, movable surfaces at the rear of the rocket helped correct small deviations. The rocket's structure was made of metal with an aerodynamic shape that allowed it to penetrate the air with less resistance. It had a warhead weighing almost a ton of explosives mounted on top. The rest of the body housed the engine, fuel tanks, control system, and guidance mechanisms. The launch wasn't simple. Each V2 required a mobile installation composed of several vehicles, one carrying the rocket, another bringing the fuel, another holding the oxidizers, and another holding the ignition system. All of these had to coordinate to mount the rocket in a vertical position, fill it with fuel, and activate the entire system. Once ready, ignition was carried out from a command post using long cables, located away from the launch site for safety reasons. The first successful launch of a complete V2 was on October 3, 1942. It took off from Peenemünde, climbed to an altitude of more than 80 kilometers, and landed 190 kilometers from the launch point. With that, the Germans proved that their project worked, and that the idea of an intercontinental ballistic missile was no longer science fiction. From that moment on, it began mass production with the idea of using it as a weapon of retaliation against Allied cities. Once the V2 was in action, there was no stopping it. Upon ignition, it climbed in a straight line to an altitude of about 80 or 90 kilometers, then followed a sharp curve and descended at high speed. In the final stretch, the missile fell at over 5,000 kilometers per hour. When it impacted, nothing could be heard before the explosion because it was traveling faster than the speed of sound. This made it impossible to detect in time, let alone stop with the anti-aircraft defenses that existed at the time. Unlike the V1, which had a relatively slow flight and a noisy engine, the V2 couldn't be heard or seen before impact. It wasn't known that one had fallen until it had exploded. The British tried using radar to track its trajectory, but with such a short reaction time it was useless, and because it flew so high and so fast it couldn't be intercepted by aircraft either. London was the hardest hit by these attacks, although rockets were also launched against other cities, such as Antwerp. In total, the V2s caused thousands of deaths and injuries, as well as considerable material damage. Although their accuracy was limited, and their impact on the war itself was not decisive, The psychological effect was profound. People had no warning. They only heard the explosion and saw the disaster. As for manufacturing, the V2 wasn't built in ordinary factories. It was done in underground tunnels, like those at Mittelwerk near Nordhausen. There, the rockets were produced with the help of forced laborers, many of them concentration camp prisoners. The conditions were extremely harsh. Thousands died from exhaustion. Mistreatment or accidents during the assembly of the missiles. Production was organized by General Hans Kammler, who was in charge of directing the entire assembly and transportation system. The rocket was shipped by train in parts and then assembled near the launch site. This mobility gave Germany a certain tactical advantage, as it made it difficult for the Allies to detect and destroy the launch points before they were used. Once ready to fire, the process was delicate. The tanks were filled shortly before takeoff because the liquids were unstable. All electrical, pressure and control systems were checked. When everything was verified, the ignition was activated from a protected console. Within seconds, the rocket took off, disappearing into the sky in a white trail. Despite its complexity and the effort involved in manufacturing and launching it, the V2 was the first true rocket used in combat. It was also the direct origin of all modern missiles. After the war, both the United States and the Soviet Union brought engineers, plans and parts to launch their own space and military programs. The development of intercontinental rockets, satellite launches and even missions to the moon began here with V2 technology. Radar, secret signals and the electronic warfare of the Third Reich. Germany began the war with a clear advantage in remote detection systems. One of the first radars to operate was the Freya, installed at fixed stations on the coast. It could detect enemy aircraft at over 100 kilometers and provide timely warning to defense centers. Although it lacked accuracy in calculating altitude, it was useful for launching fighters into the air. Later, the more accurate Würzburg radar was developed. This radar had a parabolic antenna and was primarily used to direct anti-aircraft artillery fire. It was connected to optical and mechanical systems that helped track moving targets. Hundreds of these devices were placed in strategic locations along with searchlights and cannons. In parallel, work was carried out on radars for night fighter aircraft. The most widely used was the Liechtenstein radar, mounted on the front of fighters. It allowed pilots to find enemy bombers in the dark by using reflected echoes. This advance completely changed nighttime air operations, which had previously been almost blind. There was also a maritime radar called SeaTact, installed on warships. It worked similarly to the Freya, but adapted for use at sea. It made it possible to locate enemy ships and aircraft more quickly than through direct observation. It was used on cruisers and battleships during the early stages of the conflict. In addition to radar, the Germans worked with radio navigation devices. One of the best known was the Knickerbein system, which transmitted signals from the ground in the form of crossed beams. When a bomber flew over the crossing signals, the pilot knew to release the bombs. This was a technique for attacking with greater precision without needing to see the target. This system was followed by more complex ones, such as the X-Gerät and Y-Gerät, which combined radio and timing to calculate the exact moment of release. They were useful when weather made it difficult to view targets from the air. Although the British did jam them, the aircraft worked well for a time. When the Allies began using countermeasures, the Germans responded with improvements. The SN2 radar was introduced, a more powerful version of the Liechtenstein radar with greater range and less interference. Frequencies were also adjusted to avoid jamming. These new versions were used primarily in night fighters. The British had begun using metal strips, known as windows, dropped from aircraft to generate false radar signals. In response, German technicians developed filters and techniques to distinguish real echoes from fake ones. Even so, the saturation of space with false signals made air defense difficult. On the ground, receivers were also designed to locate enemy transmissions. One system, called Corfu, detected Allied radar signals, such as those of H-2S, used by British bombers. Once an aircraft was located by its active radar, it could be tracked with anti-aircraft artillery or fighter jets sent in search. Submarines also received warning systems. Devices were installed that warned if enemy radar was searching for them. This allowed U-boats to submerge before being detected by Allied aircraft. These sensors did not block the signal, but they did allow for a timely escape. Regarding communications, the German army used short and long-range radios with varying levels of encryption. Important signals were sent via the Enigma system, which used internal rotors to change the letters of the message. It was configured differently each day. Although initially seemingly indecipherable, the Allies later managed to break the code. For tactical use, vehicles carried smaller radios. Tanks had internal intercoms and external antennas. Platoons could speak to their commanders using handheld devices, although their range was limited. The sound quality depended on the area, the weather, and interference. Throughout the war, electronic warfare became increasingly important. It wasn't just firepower that counted, but also the ability to see first, detect first, or confuse the enemy. Germany started with an advantage in this area, but the Allies soon followed suit with advances of their own. Fritz X, Mistel, and H-293, the bombs that Germany controlled by remote control. One of the Luftwaffe's most advanced ideas during World War II was to guide bombs from an airplane toward a moving target. Until then, bombs had been dropped by eye, from a height, with luck or calculation, but with no possibility of correcting their direction once they were in the air. What German technicians proposed was to be able to move the bomb as it fell, to make it more precise. The first serious model was the Fritz X, a bomb very similar to a standard 1,400 kilogram bomb, but with small cross-shaped wings and a tail section with movable surfaces. The device was released from a fairly high altitude and controlled by the aircraft's gunner with a kind of remote, like a joystick, which sent signals by radio. To track the bomb, the tail was painted white, and the operator observed it through an optical sight. By moving the control, he could correct its path if it went off course. It was a primitive system, but it worked. The first time it was used successfully was in September 1943, when they sank the Roma, an Italian battleship that was sailing to North Africa after signing its surrender to the Allies. Another guided bomb was the HS-293, which was lighter but incorporated a small rocket motor that ignited after being released. This gave it greater horizontal range and allowed it to fly toward its target almost like an airplane. Like the Fritz X, it was also controlled by radio signals from the launching aircraft. The operator guided it remotely to the target, especially enemy ships at sea. The HS-293 was used several times against Allied convoys, especially in the English Channel and the Atlantic. The British, realizing that it was radio-guided, attempted to jam the signal with electronic jamming. This reduced its effectiveness, but did not completely eliminate it. Several vessels were damaged or sunk by these weapons. There was another, even stranger system, called Mistel, which consisted of joining two planes, a large one below, loaded with a huge bomb in the nose, and a small one above that, guided. The pilot sat in the top position, and when they were close to the target, he released the bomb plane, which crashed and exploded with a brutal payload. It was used to attack bridges, ships, and fortifications. These three types of guided bombs demonstrated that Germany was far ahead in ideas that are commonplace today. Although they were cumbersome and difficult to use, they showed that the concept of guided missiles was already in place before the war ended. Despite this, the impact of these weapons was significant. The sinking of the Roma caused by a Fritz X was a clear example of their potential. On other occasions, entire convoys had to change course or suspend operations because they knew the area was dangerous for this type of attack. The Mistel, on the other hand, was more complicated to use. As the smaller aircraft was unmanned and packed with explosives, any failure in the docking or guidance system could cause it to veer off course. It was also difficult to hide such a large aircraft, so it wasn't ideal for surprise attacks. But even so, there were successful missions, especially against bridges and reinforced positions. Nazi jets, the planes that arrived too early. One of Germany's greatest technical achievements during the war was putting a jet-powered fighter plane into the air.